So, but I'll switch to English and wish everybody welcome to the last webinar in the series about large-scale 3D printing. We're rounding it off today with the presentation from Mike Iubelt from Thermwood Corporation in the US, which is, I think one of the biggest polymer printers in the world. I'll just share my screen. There we go. So today is a big print in plastic and composites with Mike from Thermwood. And as again, this is part of the AIM Link network of official and unofficial partners, which covers everything within additive manufacturing, where we support anybody from the idea phase to the design phase to the pilot to the production with anything within concrete, ceramics, composites, metal, or plastics. And if you haven't done it already, strongly recommend you to search for AIM Link on LinkedIn, where we have a showcase page where we upload showcases, customer cases, and new partners in our network. So today's speaker is Mike from Thermwood, where you can see a photo of their printer and get a slight impression of the size and dimension we're talking about. But I'll leave all of that up to Mike to present. So if you want to share your screen, Mike.
Excellent. Thank you, Ivor. Everything coming through okay?
Yeah, it's perfect.
Yeah. First off, just a big thank you to AM Link Force Technologies. We appreciate the opportunity to discuss and show you a little bit about Thermwood and our large-scale additive manufacturing machine. I'd like to start off, just give you a quick introduction to Thermwood. Our factory headquarters are located in Dale, Indiana, here in the United States. We were founded in 1969. We have over 16,000 square meters of building space and somewhere around 115 employees. Our corporate headquarters consist of an office showroom, formal training rooms, the service support departments, engineering, and the manufacturing plant. In-house research and development, engineering and manufacturing allows us to completely control the fabrication process. Continuous product development, it's largely driven by the industry. We listen to what the industry needs and then we try and address it. Gives us comprehensive control over the product. It allows for targeted innovation. Like I mentioned, Thermwood's been in business since 1969. We started out as a plastic molding company, and through a change in our market, we got into the CNC router business in the mid-1970s. Most of the core CNC router technology that we take for granted today all originated at Thermwood. This early effort has evolved until today. Thermwood builds one of the most powerful, capable CNC controls in the world. We've also refined and improved the early CNC routers into world-class industrial machines that you see today. Along the way, we also developed and programmed sophisticated third-generation CAD/CAM software, and we are now adding artificial intelligence to our machinery. All this experience has been instrumental in the development of Thermwood's large-scale additive manufacturing system. We have experience with extrusion and high-volume thermoplastic production, the ability to manufacture high-quality, reliable industrial machinery. We have a core understanding and complete mastery of CNC controls. and experience developing specialized CAD/CAM software. Plus, we have the talent and the crew to create new, innovative technology when needed. Our approach to large-scale additive manufacturing, the key here is different. Our print process is different. The machine itself is different. The print head is different. The control, slicing software, and then the resulting parts, the end product coming off our machine. It's different than anything else out there. The LSAM uses a near net shape process where the part is quickly printed oversized and then machined to the final dimensions. It's a substantial piece of equipment. It's available with both a print head and a 5-axis CNC router. We're focused on making machines for companies that produce industrial tooling, masters, patterns, molds, and production fixtures for a variety of industries. These include aerospace, automotive, foundry, and marine. These areas have shown to have the potential for significant savings versus current construction methods. The LSAM prints at high enough speed with large enough beads that it operates at room temperature rather than requiring a heated environment. Its unique multi-servo process controlled print head weighs over 1.5 tons, yet can move up to 1 meter per second. It functions at high enough temperatures with enough torque to process difficult, high temp materials, which are proving ideal for composite tooling. The LSAM is a serious, heavy-duty machine intended for continuous operation in an industrial environment. I'll go through a quick, just a quick introduction to all our different models. We have quite a few. The LSAM 1020, that's our standard, that's our flagship model. This is a closed configuration, a high wall moving gantry machine. The table is 3 meters wide, and it's available in varying lengths up to 30 meters in 3 meter increments. As with most of our LSAM products, we have a Z-axis print height of 1.5 meters. And then on the trim gantry, you have 1.8, which gives you the ability to trim over the top of any printed parts. With the standard flagship model, you have the ability for simultaneous print and trim. And this machine's also available with our VLP, our vertical layer printing technology. And I'll dig into that here in just a few extra slides. The next machine is our LSAM MT. This is an open configuration, moving table, 3 meter by 3 meter. On this machine, you can print and trim, but not at the same time. So you're either printing or trimming. And you also have the same Z-axis print height and trim height as the standard flagship model. This model is also available with the VLP technology as well. The next machine is the LSAM 1010. This is another closed configuration, high wall, moving gantry style machine. And we're back to that 3 meter by 3 meter table size. And you can print and trim on this machine, just not at the same time. So this is a single control machine. The moving gantry carries both the print head and the trim head. And then the last machine, this was just introduced just last month. This is our lower cost, smaller machine. This is an LSAM additive printer. Again, an open configuration with a moving table. This machine is available with an enclosure, which would satisfy any CE requirements. This machine's available in 3 different sizes. What you see pictured here is the 3 meter by 1.5 meter. It's also available with a 1.5 by 3 with VLP, and then a smaller 1.5 by 1.5. The LSAM additive printer is a print-only machine with a 30 millimeter melt core. The print height is a little bit shorter on the Z. It's 1.2 meter. And then after the part has been printed and cooled, it must be moved to a secondary machine for trimming. With our machines, you can print both horizontal and vertical. Horizontal layer printing, this is standard on all LSAM models. The print nozzle is perpendicular with the printing surface or the work table of the machine. And there's a few examples there showing this. The next option is what I mentioned earlier, the vertical layer printing option. With this, the nozzle is rotated 90 degrees and a movable wall is mounted onto the fixed table. Parts are grown the length of the table rather than growing the part upwards. And this allows you to print a continuous part, which is as long as the machine table itself. Every LSAM is a complete, fully engineered system. It's ready to run, all accessories and ancillary equipment included. Each machine is configured with dryers, fume extraction, chillers, thermal imaging, slicing software, etc. Basically everything. We provide a complete package, everything except the thermoplastic material itself. Speaking of that, I mean, the LSAM is capable of printing virtually any thermoplastic polymer in pellet form. The most popular that we've come across are ABS, polycarbonate, PEI, PSU, and PESU. These materials are typically filled with carbon fiber at varying percentages, usually around 20 to 25% by weight. The maximum operating temperature of the part being printed needs to be considered when selecting a polymer. I know we have a few customers out there that are printing a cellulose-based material as well. We don't have any experience with that, but we have printed some virgin material without any fill, and then we've also printed some glass-filled reinforced material. A majority of the projects we have worked on and are continuing to work on are secret. You know, these projects are either corporate confidential, military classified. We have been allowed over the years to share a few projects, and I'll show you a few of these here to give you the idea of the type of work we've done and are still doing. This particular part here, this is a production trim fixture. It's a canoe fairing for a Boeing 777X. This part is a scaled split yacht mold. This particular part was printed with our vertical layer printing technology. And all of these projects that I'm sharing with you now, these are all available on our website or on our blog, where you can go and watch videos of these particular parts being printed and read more information about these parts. We did a submarine nose cone with the U.S. Navy Surface Warfare Center. One of our more popular products was a master plug for a boat that we printed for White River Marine Group. It's a Tahoe boat. I believe it's sold under the Tracker name, but this plug was used to create a mold, and then that mold is being used to create a production model boat, which is available for sale right now. We were involved with Local Motors. They've printed the chassis for the Ollie autonomous bus. And then we've printed a helicopter rotor blade mold alongside Bell. And this was a high temp autoclave tool. This is printed with the PESU material. And then another U.S. military project we worked on was the a mold for an engine oil drip pan on the Chinook helicopter. So we've learned a lot along the way. and we'll take a closer look here at the machine and see how we got to where we are today. And we'll start off with the print head. The LSAM print head consists of three major sections, starting at the very top with a liquid-cooled drive. This is a custom, high-torque, liquid-cooled servo motor that's coupled to a high-performance liquid-cooled gearbox, and that provides the drive power for the melt core, or the print head. The second section is the melt core. This determines the maximum output of the print head. It consists of a feed housing, an extruder, and a melt pump. It has a liquid-cooled feed hopper that feeds the polymer to the patented extrusion screw, turning inside a ceramic heated screw barrel. The patented extrusion screw and barrel does not function like a traditional plastic extruder, where most of the heat comes from the shearing action of the rotating screw. The screw speed is constantly changing in additive manufacturing, so the traditional approach means uneven heat. In the LSAM extruder, more than 60% of the heat comes from the heated barrel and not the screw, so polymer heating is more even. You need to be able to control and modify all aspects of the print process dynamically while printing. Precise print bead dimensions are an absolute necessity for really quality printed structures. This is not just possible with traditional extruder. A common problem with plastic extruders, even in steady state operation, is uneven output flow, called surging. The LSAM outputs flow from the extruder into a polymer melt pump. This servo-driven fixed displacement pump precisely meters the heated polymer to the nozzle, forming a precise, consistent print bead. A sophisticated, patented servo process within the control monitors and automatically controls the relationship between the extruder and the melt pump. The final section of the melt core is the compression wheel. The compression wheel uses a patented process to automatically follow the nozzle tip as it prints. The bead is formed, compressed, and completely fused with the previous layer. This creates a solid void-free structure that is not possible with any other approach. The resulting layer dimensions are very precise and very consistent. Those dimensions are 21 millimeter by 5 millimeter. The LSAM is available with three size melt cores. The smaller LSAM additive printer, like I mentioned before, comes with a 30 millimeter melt core. It has the ability to process up to 45 kilograms of material per hour. The 40 millimeter melt core, that's our standard melt core, and that's just about right for most applications today. That comes standard on all our other equipment, including the LSAM 1020, the MT, and the 1010. This processes up to around 90 kilograms of material per hour. And then on our standard flagship model, the LSAM 1020, there's an option to increase that melt core up to 60 millimeter, which will allow you to process up to 225 kilograms of material an hour. The 40 and 60 millimeter melt cores are interchangeable, and that allows you to achieve different output levels from the same machine. Those melt cores can be swapped out in about 6 to 8 hours time. And all our melt cores are designed for operation up to 450 degrees Celsius. You need a big print head for high output and big beads. Big beads work better than small beads. Fewer passes, better layer fusion, easier thermal management. With bigger print heads, everything gets bigger, including the minimum size part you can print. A high output print head, printing big heads, works at room temperature. You do not need a heated table or a heated print environment. Additive manufacturing this way is essentially an exercise in controlled cooling. Polymer cooling and not print head output determines the print speed. The printed layer must cool to within a specific temperature range before the next layer can be printed. It must be cool and stiff enough to support the next layer without distorting, but it must be warm enough to completely fuse with the new layer. Automatic layer time control. This controls the feed speed to automatically maintain a constant print time per layer. The printed layer temperatures are measured with a thermographic camera or the new thermal sensor, which we just introduced a few weeks back. The thermographic camera displays the layers in the color green if it is within the proper temperature range for that specific polymer that's being printed. The new thermal sensor layer automation system continuously measures the temperature of a printed layer just before a new bead is added. This allows the machine to automatically adjust the feed speed using layer time control. So, polymer cooling dictates both the shortest and longest possible print time per layer. The time it takes to just cool enough is the fastest you can continuously print a layer. You can't print layers any faster, even with more deposition capability. The time it takes to cool to the minimum temperature is the most time you have available to print a layer. In this case, print head output determines how much bead can be printed in the time available. So deposition capability doesn't mean you can print parts faster, but it does mean that you can print larger parts. There are, of course, some limitations. You can't just print on air, and you can't print just anything. If you stop printing and the part cools, we have found no way to reheat and start that print again. The maximum wall angle you can print is between 40 and 45 degrees, depending on the polymer being printed. Get into a little bit of the control here real quick. The LSAM uses Thermwood's Ultra 6 Super Control. It's one of the most powerful, capable, and flexible controls in existence. On the print side, this control has been enhanced with a myriad of features specific to Thermwood's print head and print operation. A few of these features are the automatic and manual bead width control, layer timing control, automatic load and unload, as well as automatic start and stop, thermographic imaging and sensing with recording and history reporting, manual print speed adjustment, and material parameters. The control is integrated with a Siemens temperature control module to set, monitor, and control the temperatures of each of the 7 heat zones. A process control that operates independent of the CNC program controls the relationship between the extruder and the melt pump. This happens automatically. The relationship is different for different materials. This relationship is established when a new material is qualified and becomes part of the parameters for the material. Other process controls that operate independent of, but in conjunction with, the CNC program include coordination of melt pump output to machine motion and coordination of the compression wheel orientation to the nozzle motion. Again, this all happens automatically, but they do react to what the CNC program is doing. The control offers the operator the ability to view and modify all operating parameters dynamically while printing, including print speed and the bead width. Pretty much nothing is fixed. If there is a variable, we give the user the ability to adjust it. Anything that is important to the actual print operation can be changed during the print process without having to stop. Not only is the Ultra 6 control capable and powerful, it's easy and intuitive to use. It is truly suitable for operation in a typical production environment. Routine things such as starting and stopping, which involve a lot of coordination between the print head, the temperatures, pressures, this has all been automated and can be accessed with the press of an icon on the screen. This includes the load melt, empty melt, hot hold, purging, layer times. The next important feature, obviously, is the slicing software. We took a look at a lot of the existing net shape slicing software that's out in the market today, and it just doesn't work well for near net shape applications with large beads. While it can be made to work for vertical walls, it breaks down as the angle increases. It requires substantial programming effort to build in the trim stock. It just doesn't work very well. You really need software intended for near net shape operations. And the only answer was to develop software specifically for industrial near net shape printing. And that's exactly what we did. Our slicing software is LASM Print 3D. It's a CAD-based program that operates within Mastercam, preserving all its rich features and capabilities, but adding professional near net shape slicing capability. We are continually developing and refining this software. Most of the additive software today uses an STL format exclusively. This STL format was developed as a computer display format, and it doesn't really work well for defining industrial parts. The LASM Print 3D uses real CAD formats, solids, surfaces, anything that loads into Mastercam. It offers a lot of choices in boundary, infill, and solid layers. The final step is the trimming. The flagship LASM 1020, that's, like I mentioned before, it's a dual control, dual gantry system with the capability for simultaneous print and trim. The smaller LASM 1010 and MT versions, like I mentioned, those have a single control with both the print and trim heads mounted on the same gantry. They can print and trim, just not at the same time. The 5-axis CNC router head performs the trim operations to take the printed part to the final net shape. Our machine features a 9 kilowatt, 24,000 RPM spindle with an automatic tool changer using an HSK 63 tool holder. Their trim head can reach around the entire machine envelope horizontally, as well as from the bottom of a printed part completely over the top. We use a 3-dimensional laser compensation. This assures the best possible positional accuracy. And then the high tolerance tool length measurement system. This is used to measure your tools prior to the machining or the trimming process. And that's the final link to achieving accurate dimensions and high quality tooling surfaces on printed parts. It's vital when you're blending surfaces using different tools. Our exclusive patented impact resistant head means you will seldom, if ever, need to realign or repair the 5-axis head after an inevitable head crash. A boundary wall, which consists of 3 layers of heavy clear vinyl, as well as a light curtain, separates the print from the trim gantry. This wall can be moved to any position between the gantries where it defines the working envelope of each side. And this is only available on the flagship model with the simultaneous print and trim capacity. And then, like I said, this allows the ability to print and trim on the same machine. And it's an important capability to an additive manufacturing system, allowing for functions that can't be done any other way. So that's just a quick overview of the LASM systems by Thermwood. You know, this is disruptive technology and it's changing industries. It's not something that's going to happen in the future. This exists and is happening right now today. There is no future without additive manufacturing. And I thank you very much for your time.
Yeah, thank you very much. Great presentation. I can hear myself. Better now. No. I'm just going to mute here because I'm hearing myself. But thank you very much for your presentation. A great overview of the LASM system and the possibilities of what the machines can do. I see we have 2 questions, but I'm just going to introduce our fourth specialist for this webinar. He's going to do a short presentation on quality assurance of 3D printed parts in polymers, and then we'll head over to the questions. So, Jonas, are you ready?
Can you hear me?
Yeah, I can hear you.
I'm ready.
Yeah, I'll share my screen again.
Hello everyone, my name is Jonas Hansen and I work as a polymer specialist here at Force Technology. I would like to give like a brief overview over some of the options we have for quality assurance of 3D printed materials. And one of the things that we used a lot when we quality test 3D printed materials are we using tensile strength, we're measuring tensile strength and elongation break. And one of the things that's very interesting to look at here is to see how strong are the adhesion between the layers. So, for example, it's very interesting for us to measure the strength in all the different directions in X, Y, Z directions to see where the material is like strongest. And this is often, we see that is often have an influence by how the printing has been done on the material. What we also can do is we can expose samples for cycles in what we call the climate chamber, where we have the opportunity to control the temperature and the humidity of the air, and it can also go to below freezing points. So we can see the effect of what would happen if we expose our products to high humidity, so moist can migrate between the printing layers, and then we can see how this will affect the performance. We can also use this to check what would happen with the product if we get below TG for some of the materials used for 3D printing, and how it will affect the samples. And also we can also use like some impact test to figure out after we have done this climate testing how much energy is required to then see a fracture in the sample, and then we can compare if it's still very resistant after it's been exposed to these different cycles in the climate chamber, or if it's been like significantly worsened. This is some of the tests that's like more focused on the 3D printed materials, but we also have like tests for like the general plastic products that might also be useful in 3D printed materials. So we, for example, do have like a thermal analysis of the polymer to find melting points and stuff like that. And we can also characterize which kinds of polymers has been used by spectroscopic methods as well. So yeah, I think that was like a brief introduction to what we.
Perfect. Offer. Thank you. Thank you very much, Jonas.
You're welcome.
Yeah, let's do the question here. I see Michael Nystrom is asking, are there any plans for printing wings for windmills in new composite material combinations? We have one project because the Thermwood printer is not very broadly commercially available, but we have through Aimlink one partner which we can commercially print through. We are in works of figuring out 3D printing with windmills, but due to confidentiality, I can't disclose any more information on that. But if it's a specific case you have, Michael, write to us at or aimlink@force.tk or directly to me, and we can have a meeting and see if this is something that we can help you with. Yeah, I see Stephen Smith is asking, how about supports and support removal? this becomes more problematic with bigger beads. Do you have a solution for this? You know, if you have a comment, Mike, I guess you don't print with supports, but rather machine it.
Yeah, we've attempted over the years, as we're learning more about additive manufacturing, we've attempted to add some support structures into our prints. We have not been successful with that at this time. You know, we've tried aluminum, we've tried some honeycomb, both paper and aluminum, and it just at some point, I'm sure we may get to there, but right now we're not adding any support structures to any of our prints.
Yeah, and I guess also that the vertical layer printing also removes a bit of need for support if we're printing in the x-axis.
I'm sorry, what was that?
Yeah, when you're printing with vertical layer printing, you're printing from the wall and straight out. So I guess that eliminates the need for support in many cases.
Yeah, certainly you can add infill if you need support inside your structure for extra strength.
Yeah, perfect. Did that answer your question, Stefan? Yep, he says thanks, perfect. We have Martin asking, why not just print directly instead of making a mold first?
Well, you certainly can print a part directly, if depending on the part that you're wanting printed. But the major savings, the significant savings with time and material, that's really geared towards the tooling, the molds, fixtures. What we're typically seeing is usually around a 70% savings in time and about a 30% savings in material. So I mean, it's a drastic savings that can be achieved just with the tooling itself. But we do have some customer of ours that are printing end use parts. So they're printing large, and I've got to be careful, some large display pieces for some architectural firms. So there is customers out there that are printing end use parts directly. And like the chassis for one of the slides I had in there earlier, the chassis for the autonomous bus, Ollie from Local Motors, that's an end use part. So they're using our machine to print the chassis for those buses.
Perfect, thank you. Martin also follows up with a second question. What CAD software are you criticizing for not being a real CAD program with only STL files? I'm not really sure that I'm criticizing any CAD programs. I'm not too familiar with the software side of things. The way I understand it with the NetShape printers, those use an STL file, and we've just not had very much luck importing those into our slicing software, and it just doesn't really scale up for large scale additive manufacturing with the near NetShape process, where we're printing oversized and then we're coming back and machining typically about 6 millimeters away from the final print to get to the net shape of the part being printed. Ah, okay. So there's a little bit of like a translation issue when you're upscaling the STL to gain the extra material.
Exactly. Yeah.
Okay. Perfect. Thank you. Then we have Bo Paulson who asks, do you work with recycled materials from your own prints? So I think what he's asking, if you print and you don't want to use that print, can you recycle that and print it again?
We have not tried that. We're told by the polymer companies that it is possible. One thing that you really have to pay attention to, and us here at Thermwood in our demonstration facility, one day we may be printing ABS, the next day we may be printing polycarbonate, PESU, the high temp materials. If you're going to recycle those materials, it's very important that you keep those materials separate. And when you do your trimming operation, that creates chips. And so you would have to thoroughly clean those chips up before switching to the next material. But we're being told it is possible to blend in the recycled material with a virgin material. but we've not wanted to introduce that into the development of this just yet, but we're told it is possible.
Yeah, okay, it's always nice to be able to recycle failed prints. Did that answer your question, Bo?
Yeah, you know, the different materials, obviously they have different melting points. So you cannot mix the ABS in with the PESU material. You have to keep those separated. And then those can be blended back into recycled material.
Yeah, perfect, thank you. See if there are any questions I missed. Are there any more? Yeah, there we go. Martin says, okay, fair, but Autodesk Inventor and others can import and convert files. I get compatibility is a concern. I don't know your slicer software though.
Yeah, the LASM Print 3D, I'm not familiar with the Autodesk Inventor, but our LASM Print 3D slicing software, we developed that in conjunction with Mastercam. We have a very good long relationship with Mastercam. So that is an actual add-on that runs inside of the Mastercam software. And you can, you know, we've got a good resource on our website at thermwood.com under LSAM. There's a section of what is LSAM, and that's a very good starting spot. There's a lot of information in there, and it'll help get you pointed in the right direction. There's also a section in there about the slicing software that'll give a little more information than I'm prepared to give today.
Yeah, that's fair. He says, thank you. So I guess that answered here. Let's see. Jonas is asking, are you able to show any strength values of these printed materials reinforced with carbon fibers? He's a material engineer.
Yeah, we've worked closely with Purdue University. They're a major university here in the state of Indiana. We've worked closely with them throughout the development of this machine. We've printed quite a few samples for them, and they've tested those. That information is available. It's not located on our website or out into the public just yet. But if you drop us a line at sales@thermwood.com, I'd be happy to forward some of that information along to you.
Let's see if there comes another question here. Jonas, do you have any questions or thoughts or concern from your perspective as a polymer specialist?
Yeah, I was wondering, now that you talk about recycling used or failed prints, since they haven't been used, wouldn't it be like kind of easy to like sort them in each kind of polymer type and then use them for recycling later on, and then maybe discard all the small scraps that you were talking about?
Certainly, yeah, that's certainly a possibility. So if you've got an ABS tool, a room temperature tool, you know, that you've printed, trimmed, you've used that for 3 months and you're done with it, you'll never use it again. Certainly that part could be scrapped and recycled and turned into new pellets.
Yeah, great question and an answer. Let's see here. Martin asked, how well does your software work with importing models, drawings, and assemblies from other softwares, specifically CAD software?
Yeah, I mean, like I mentioned before, our LASM Print 3D, it runs inside, it's an add-on to Mastercam software. So any solids, any file can be loaded into Mastercam. We'll work with our LASM Print 3D software.
Yeah, perfect. Let's see here. Bo is asking, what is a typical cool down period for 40mm TIG walls before you can trim it? He benchmarked your process some times ago, and cooling was a major part of the process time.
Yeah, it certainly is. Obviously, the part has to be cooled before you can final trim it to the net dimensions. Here at Thermwood, typically we're not a production environment, but what we usually do is we print one day, and then we start trimming the following day. So we let it cool overnight. We have printed and worked on some smaller projects that we just let cool for 3-4 hours, and they were fine. And it was, cooled enough to where you could start the trim process. But typically we let parts cool overnight and then start the trim process the next day.
Yeah, I think I'll have a follow-up question there. Is there any way that you figured out how to accelerate cooling?
We have not, no.
No. Okay, so you can't just put fans on and increase it, or?
Yeah, I'm not sure that you would want to put fans on it, just because you're going to get uneven cooling. I think it's our experience. It's best just to let the part set and cool. We don't blow any fans across it or push any cool air towards it.
Sounds great. Let's see, another question from Bo. Mastercam is a good platform for import of most 3D formats. This is mainly due to their CAM history. Yes, I think that was more of a statement. Martin asked if there's a trial version to test out software or a hobby version.
Martin, unfortunately, there is not.
And then I think with the Thermwood LASM printer, there is only one commercial available printer in all of Europe. So most of your customers are using your machines for in-house printing. Isn't that correct?
I believe we have 3 customers right now that offer a service bureau. So you can approach them with a potential project that you're wanting to manufacture with a LASM system, and they'll work with you and provide you with a quotation and possibly print and trim that part for you. The one that you referenced in Europe, they are a print service. They're also a material blender, so they provide material as well. And then we have a couple here in the States, Ascent Aerospace, they're a customer of ours. They offer a print service for hire, as well as Legacy Industries.
Yeah, perfect. Thank you.
And I'm sure there'll be more and more joining your network very soon.
Yeah, I'm looking forward to it. A fleet of LASM flagships would be nice. Yes. Yes, we are about to get closer to the 1 hour mark. Are there any final questions that you would like to ask Mike? If there are any other questions, you can also email them to us. I'll put my contact information on the screen shortly, and then you're more than welcome to write us.
Yeah, and feel free to visit our website at thermwood.com. All our contact details are there. And if you just shoot us an email at sales@thermwood.com, that'll get directed to me, and then I can follow up with any additional information or questions you may have.
Yeah, it looks like that was it. I'll share my screen again. So yeah, back. So thanks to everyone for everyone who's been here for all the webinars. Thank you very much for your patience, and we're hoping that it's been a learning journey, that you learned and gained a lot of new knowledge that you can use in your work and can create some great projects from it. My contact details are on the screen, so if you want to ask more about any of the previous webinars or this current one, feel free to write me. You can also call me, and I'll happily answer those questions or forward you to our speaker. So thank you very much, everybody, for participating, and have a nice evening.